So the last thing from last time I was talking about this theorem. So I explained how the Weyl group W of a root system was generated just by the simple reflections S1 through SL, subject just to the relations SI squared is 1 and SISJ to the power MIJ is 1. So this is for all I not equal to j. So where here this MIJ, these were either 2, 3, 4, or 6, according to the rank 2 root system containing alpha I and alpha j there. So it was 2 if it was A1, 3 for A2, 4 for B2, and 6 for G2. So this was this Coxeter presentation. For the Weyl group, so showing that the Weyl group is a Coxeter group. Now, I'm kind of trying not to prove everything in this chapter, so I started out, that very first theorem that I gave you, I fed you was that there was this bijection between chambers and bases, sending chamber C to bases delta C, so I skipped the proof of that. That's completely self-contained proof in section 10.1 of Humphreys. But last time I did carefully prove that there was a bijection between the Weyl group and the set of chambers, and between the Weyl group and the set of bases, just given by the action on the fundamental chamber or on the base corresponding to the fundamental chamber. So we were kind of at that setup. Oh, and I also carefully proved that the Weyl group was actually generated just by the simple reflections. So I'm trying to kind of prove the main fundamental facts that you need again and again and again, but skip a few things along the way. I did not prove that this was a complete presentation for the Weyl group. I showed that the simple reflections generate, and I showed that all of those relations held, but I did not prove that that was a full set of relations. And actually, that's not something we're ever going to use, but of course it's a pretty fundamental and basic fact about root systems that you get the Weyl groups are Coxeter groups, special Coxeter groups. But anyway, so that's where we're at. I think I decided that I maybe numbered the B2 root system wrong, so let me just kind of tweak that just a little bit. I just want to switch my labeling of alpha 1 and alpha 2 around. I think that just becomes more conventional. So I'm just switching alpha 1 and alpha 2 around, so otherwise nothing changes there. So there are going to be 2 more lemmas that I'm actually going to try and prove, in my goal to prove all of the main important facts, but skip some of the big theorems that you can take on trust. So the next lemma is to do with something called length. The length L of W of an element of the Weyl group is the minimum of all R's such that you can write W as a product of R simple reflections. Okay, so we've proved that the simple reflections generate the Weyl group. So every element of the Weyl group can be written as a product of simple reflections. And if you take the shortest such product, if you just need R simple reflections at the smallest, that number R is the length of W. Blue here, there we go. Then that's what's called a reduced expression for W when you actually achieve that minimal length. The smallest number of simple reflections multiplying together to give W, that's called a reduced expression for the Weyl group, for the Weyl group element. And so what I wanted to prove was another description of the length. The length of a Weyl group element, I've defined it just as this shortest number of simple reflections that you need to get the Weyl group element, but it's also the size of the set of all positive roots such that W of alpha is a negative root. Does the number of positive roots sent to negative by W. An equivalent description of that last one, I'm not going to prove this, this is easy to see from the definitions. That's just the same as it's the number of positive roots such that the fundamental chamber and W applied to the fundamental chamber are on different sides of the hyperplane alpha perp. That's just, that second formula is just a reinterpretation of the first formula. It's easy to prove that equality. This one's sometimes useful if you're thinking in terms of chambers because it's a little bit more geometric in nature. So if we were looking back at our rank 2 root systems, so there's the fundamental chamber. This chamber I would label by S1. This chamber I would label by S2. And this chamber is labeled by S2, S1, which equals S1, S2. That's length 1, length 1, length 2, because there's 1, or 2 hyperplanes separating that chamber from that chamber, and so on. So in G2, that's length 0, length 1, length 2, length 3, length 4, length 5, and then that vial group element there, that's length 6. That'll be the longest element of the vial group, that kind of labeling that furthest chamber away from the fundamental chamber. Okay, so hopefully that makes good sense. So let's prove the lemma anyway. So that we're going to go by induction on the length. If the length is 0, well then W is just the identity and it's kind of trivial. So now let's assume that W is not 1, and let's let W be SI1 up to SIR be some choice of reduced expression. So the length of W is this R. And let's let N be the number of positive roots sent to negative by W. Okay, so our goal is to show R equals N. I'm going to let W prime be W times SIR. Okay, so this is just SI1 up to SIR minus 1, and this must be a reduced expression. I mean, if you could write W prime with fewer than R minus 1 reflections, just multiply by SIR and you get an expression for W with fewer than R simple reflections. So this shows that the length of W prime is R minus 1. Now let me see. We must have that W prime on alpha IR. What is that? That's SI1 SIR minus 1 alpha IR. It must be a positive root. Otherwise, you could apply lemma 6 to rewrite this element of the vial group as a strictly smaller number of simple reflections. And that would contradict the reducedness of our expression, the minimality of R in these expressions. But if that's a positive root, then this guy here, W of alpha IR, which is all of those guys with one more S, that's going to be just minus the one on the previous line. That must be a negative root. Okay, so I want to compare how many positive roots W sends to negative with how many positive roots W prime sends to negative. And so what we're seeing here is that the simple root alpha IR, W prime keeps it positive, but W sends it negative. So there's one more guy that W sends from positive to negative. And in all the other positive roots, well, SIR just permutes them amongst themselves by, I think that was lemma 5. So that means that all of them, the number of them that's sent to negative by W must be the same as the number that's sent to negative by W prime. So now if we apply that lemma 5, we deduce that W prime sends just one fewer, so n minus 1 positive roots to negative. Hence, now we've got that the length of W prime is less than the length of W. We can use induction to get that the length of W prime, which is R minus 1, is equal to that number of positive roots it sends to negative n minus 1. Therefore, R equals n, and we're done. Let's do an example of this. I've used these rank 2 root systems a lot. I think it's time we went up to some bigger rank. So let's talk about the root system AL. So when I do this, I always find it convenient to set n equal to L plus 1. So I'm just going to define this root system. So I need a Euclidean space, and it's better to start with a slightly bigger Euclidean space than we actually want. I'm going to call it E hat. So I'm going to make this into a Euclidean space so that these epsilon i's are just orthonormal. Right, so this is just an n-dimensional vector space with basis epsilon 1 through epsilon n, which I'm going to just make those orthonormal to make this into a Euclidean space. And then the actual Euclidean space of dimension L that I want is going to be the sum of all of those epsilon i's perp. So that's just the set of all ai epsilon I kind of trace 0, so that the sum of the coefficients is 0. So that's how I think of it, as sort of the trace 0 vectors in E hat. So that this is a Euclidean space. Of dimension 1 less, so dimension L. So that's going to be the rank. This L is always the rank. I reserve that letter. And then I need a set of roots. So R is going to be the set of all epsilon I minus epsilon j, I and j between 1 and n, with I not equal to j. So yes, these are definitely trace 0 vectors, so they live inside E. Let's think about the reflection. So for each of these guys, we need to understand this reflection. Maybe I let S hat from E hat to E hat be the reflection in epsilon I minus epsilon j perp. And then I'll let S epsilon I minus epsilon j be the restriction of this thing down to E. Thing is that this S hat is easier to understand. It just flips epsilon I and epsilon j, and it fixes all other epsilon k's. Okay, that's just very easy to check from the formula for reflection. Hence, S hat preserves this trace 0 subspace that's E, and that's the best way of understanding that reflection S in epsilon I minus epsilon j. You just take your vector in E, you write it as a linear combination of the epsilons, and then this reflection, S epsilon I minus epsilon j, it just flips epsilon I and epsilon j. So using this, it's easy to see that this reflection leaves the set of roots invariant. So now you just check that axioms 1 through 4, axioms of root system, all hold. I just kind of did the hardest one, which was axiom 3. The others are all quite clear. So this gives us R sitting inside E, a root system. This is called the root system AL. This is a very explicit construction. And while we've got this example, let's think, what is the Weil group? Well, we've got that W actually is generated by these reflections. It actually acts on the space E hat, the whole of this one bigger dimensional space, and there it's clear what W is, right? This S hat, epsilon I minus epsilon j, is just flipping epsilon I and epsilon j. So it's clear that from this description, that W is just the symmetric group Sn, and E hat is its natural permutation representation. Right? Sn acts naturally on the set of n elements, and then E hat's just that set of n elements linearized, made into a vector space. E was the trace 0 part, and then it's got the span of this other vector as a complement on which, if you're permuting the epsilons, that's just a fixed one-dimensional space under the action of the symmetric group Sn. So this gives us this reflection representation E of the symmetric group Sn. So there's the Weil group. It's just the symmetric group Sn. What else can I do? I should pick a base. Well, alpha I, you just take it to be epsilon I minus epsilon I plus 1. And then every root, like, I don't know, epsilon 2 minus epsilon 5 is epsilon 2 minus epsilon 3 plus epsilon 3 minus epsilon 4 plus epsilon 4 minus epsilon 5. So if you have a root, an epsilon I minus epsilon j, where I is less than j and they're not neighbors, you just can get it as a sum of simple roots. So those guys give you positive roots, the epsilon I minus epsilon j's, where I is less than j, between 1 and n, and those are obviously positive sums of simple roots, and then the negative roots are just minus the positive ones, of course. So here's a nice choice of base, and if you make this choice, then you get a notion of length of an element in Sn. Well, it's just by the lemma 7. It's the number of positive roots sent negative by W. So it's just the same as the set of number of pairs I less than j, such that W of I is bigger than W of j. And that's the usual length of a permutation, which you've probably seen before in the symmetric group Sn. Number of positive roots sent negative by W. Okay, so in this type AL root system, these are all hopefully familiar notions. Okay, so that's a good example. Now I want to move towards the classification. So the last definitions are related to that. So I'm going to introduce the Cartan matrix of R. It's the matrix alpha I, alpha j check for 1 less than or equal to I and j less than or equal to L. So it depends on the choice of base, because knowing what the simple roots are, that involves knowing the base. So this definition of Cartan matrix involves knowing what the simple roots are, but actually, as all bases are conjugate, under the action of W, the Weil group acts transitively on bases. The Cartan matrix is independent of the choice of base up to reordering alpha 1 through alpha L, up to that chosen ordering. So that corresponds to reordering rows and columns in the Cartan matrix. And I'll call our root system R indecomposable if you cannot partition R as R1 disjoint union R2 with R1 and R2 not empty, so that all the roots in R1 and all the roots in R2 are orthogonal. Last lemma that I'm going to prove for you in this chapter. The following are equivalent. The root system is indecomposable you can't order the base so that the Cartan matrix splits into blocks. With blocks down the diagonal and zeros off the diagonal. And the third property, the reflection representation E is an irreducible representation of the Weil group. Okay, so let's kind of quickly prove this. So I'm going to actually prove the negations of all of these statements are equivalent. So I'm going to prove that 2 implies 1. So I'm going to show that the negation of 1 implies the negation of 2. So we're going to assume that R is decomposable. And then you just have to let delta 1 be the intersection of the base with R1. And delta 2 be the intersection of the base with R2. So delta is the disjoint union of these guys. And then you just look at the Cartan matrix. So you just order your Cartan matrix so that delta 1 comes first and delta 2 comes second. Everything in delta 1 and delta 2 are orthogonal. So these alpha I, alpha j checks are certainly 0. So that proves that not 1 implies not 2. Then I got to go that, let me see, I want to do 3 implies 2. So again, I'm going to prove that not 2 implies not 3. So given a way of splitting the Cartan matrix as above, you get a partition of the simple roots into non-empty subsets so that all inner products of guys in delta 1 with guys in delta 2 vanish. I'm just going to let E1 be the R span of delta 1 and E2 be the R span of delta 2. Because the base delta is a basis, the vector space E is then E1 direct sum E2. And now you just take some alpha in, let's say, delta 1. And if you've got alpha in delta 1, then the reflection S alpha, just by the formula for reflection, it fixes E2 pointwise. And so you deduce, and similarly, if alpha's in delta 2, S alpha fixes E1 pointwise, and it leaves E1 invariant in there. So you deduce that actually this decomposition E is E1 direct sum E2 is decomposition as modules for the Weil group, where here I'm using also the fact that W is just generated by the simple reflections. It's enough to show this for every simple reflection. So that does the job. And then what have I finally got to do? I've done, let me see, I've done 2 implies 1 and 3 implies 2. So I've got to do 1 implies 3. Again, I'm going to show that not 3 implies not 1. So suppose E is reducible, and let's let E1 be an RW submodule. Then E is E1 direct sum E2. E2 is just the perp of E1, right? We're in a positive definite inner product space here, so the perp gives us a complement. And because W is acting as reflections, it preserves the bilinear form. So because E1 is W stable, so is E2. So this is a decomposition as RW modules. So that means that for any alpha in the root system, S alpha of E1 is E1 because it's a submodule. And from that, it's easy to see that either alpha's in E1, right? So I'm just thinking about the formula for S alpha. If alpha's in E1, then when you apply S alpha to any vector in E1, you just get that vector plus a multiple of alpha. But if alpha's not in E1, well, when you apply S alpha to a vector in E1, you would leave E1 unless the inner product of alpha with that vector is 0. I've just shown that either alpha lies in E1, or if it doesn't, well, it's got to be orthogonal to E1, so it lies in E2. And similarly for E2, so this shows that R decomposes as R1 disjoint union R2, where R1 is R intersect E1 and R2 is R intersect E2, and that gives you a decomposition of your root system, showing that it's not an indecomposable root system. Okay, so that's that lemma. It's kind of just really kind of a routine bunch of checks, but there's different ways of characterizing indecomposable root systems. So now I'm finally ready to state the classification of root systems. So I'm going to skip the proof of this because it's actually rather long. And as I said at the beginning, what I've tried to do is kind of give you all the kind of foundational ingredients, the kind of important lemmas about root systems that you apply again and again and again. These properties about the Weil group, like length and height and all of this stuff. but I'm going to skip the proof of the classification theorem itself because it's kind of lengthy, and maybe that's the bit that you don't learn so much from. So I'm virtually at the point that I can tell you the classification of root systems. We still need to know what we mean by classification. So we need the notion of isomorphism. So let's take two root systems, R and R prime. And isomorphism between them is a linear map, linear isomorphism between those vector spaces E and E prime, such that F takes R to R prime bijectively, and moreover you have the following property: alpha beta check is F of alpha F of beta check for all alpha and beta in R. So on the left hand side that's the inner product on E, on the right hand side that's the inner product on E prime. Maybe I'll put an extra prime there to really clarify that. I am not insisting that this F here is an isometry. I'm not saying it preserves that it respects these bilinear forms. I'm only talking about these integers, these alpha beta checks, which remember are really ratios. So you're allowed to rescale in this notion of isomorphism. If you have an isomorphism, it certainly tells you that F induces a group isomorphism between the vial groups. That'll take the reflection in the hyperplane orthogonal to alpha, alpha in R, to the reflection in the hyperplane orthogonal to F of alpha. Maybe I'll put an S prime there, so you know I mean reflection in W prime. Or if you want in terms of the general vial group elements, it's just conjugation by F here. And if you use this isomorphism just to identify W and W prime, then the original linear map from E to E prime will actually be an isomorphism of RW modules. So let me see if the root systems are actually indecomposable. So in that case, these Euclidean spaces are just irreducible representations of RW. Well, then you could deduce using Scher's lemma, more or less, that this F is just an isometry up to a scalar. That's a term I just made up. I mean that you can show that it's not the case that alpha beta is equal to F of alpha, F of beta prime for all alpha and beta in E. That would be isometry. It's isometry up to a scalar. So you have this for some positive real number. That's really the point of this definition of isomorphism between root systems. We don't mind rescaling by some positive real number. That doesn't make any difference to the actual structure of root system. So we're just trying to allow that sort of rescaling by only insisting that these integers, these alpha beta checks, are respected by that vector space isomorphism. Okay, so now to classify root systems, of course I mean classifying up to isomorphism in the sense I just defined. It suffices just to classify the indecomposable ones. Then a general root system will just be defined by taking the direct sum of the Euclidean spaces in each of the indecomposable ones and taking the disjoint union of the indecomposable root systems in the obvious way. Moreover, any root system is determined uniquely up to isomorphism by its Cartan matrix up to reordering, rows and columns. Maybe that needs a little bit of an explanation, so let's maybe just explain that quickly. I mean, given the Cartan matrix C, let's assume without loss of generality that it's an indecomposable one. You get E back up to isomorphism by just taking, if C is an L by L matrix, you just take E to be the R span of L vectors, alpha 1 through alpha L, corresponding to the rows and columns of the Cartan matrix C. Then you know, you don't know E as a Euclidean space yet, you merely know it as a real vector space, but you know there's some inner product on it, and you don't know the alpha I alpha j's, but you know the alpha I alpha j checks for all I and j, and this determines the inner product on E up to rescaling by some positive real number. Okay, so that's allowed up to our isomorphism of root systems. So now we've got the Euclidean space. Then the Cartan matrix C gives you all the simple reflections in those alpha i's. For that, you just need these quantities, right? To know those simple reflections. Hence, you get the Weyl group W because that's generated by all the simple reflections. And then, so finally, you get the whole root system because it's just the union of the Weyl group of all translates of the base which you started with. Right, that follows, we saw that last time, any root belongs to some base, but all the bases are conjugate under the Weyl group. So any root is W conjugate to one of these simple roots. So once you've got all of this data, you can recover the whole root system, and so thus I've recovered the root system out of its Cartan matrix. Right, so it's a slightly clumsy business, but that's good enough for our purposes. Final observation of this nature. So now we're just trying to classify the Cartan matrices coming from indecomposable root systems. Final observation is that in an indecomposable root system, there are at most two different root lengths with the ratio long to short when there are two being just root 2 or root 3. I think that needs a little bit of justification as well, so let me kind of explain how you see that. Let's suppose, well, we know that if you have two root lengths, the ratio long to short is just root 2 or root 3 by our work on rank 2 root systems. So all we have to do is just show that you can't have three different root lengths. So let's suppose there are three root lengths in our indecomposable root system R. So let's let there be alpha, beta, and gamma. Let these be roots of three different lengths, and let's say that alpha is the shortest one, and that gamma is the longest one, and beta is the middle one. Okay, I'm trying to get just a contradiction here. Because it's an indecomposable root system, E is an irreducible representation of the Weyl group. So the W conjugates of beta span E. It follows that you can't have that alpha W of beta is 0 for all W in W. And so if you just replace beta by a conjugate, you reduce to the case that alpha beta is non-zero, and similarly you get alpha gamma is non-zero. Okay, so now let's think, what do we know about the ratios of these root lengths? Now that they're not orthogonal, we know that this root length with these fall into a rank 2 root system, and so we know that this must be root 2, and the other ratio, root gamma over alpha, gamma is the longest one, that must be root 3. But then the ratio of the length of gamma over the length of beta is root 3 over 2, and you get a contradiction to the rank 2 situation again. You might have to replace gamma by some conjugate gamma prime with beta gamma prime non-zero in doing that, but that gives you the contradiction that finishes that argument. So the upshot of all of this discussion, I'm kind of moving fairly swiftly through it, the upshot is that you can encode the data of an indecomposable root system not by its Cartan matrix, but simply by what's called its Dynkin diagram. So this becomes a convenient graphical way of representing all of these indecomposable Cartan matrices. So what's the Dynkin diagram? This is it's a graph. It's got vertices I. This is the index set of the simple roots as usual. And then there's going to be an edge joining I to j, or maybe a double edge, or maybe a triple edge. This is going to be if, so remember the cases in our usual rank 2 setup, it's all according to these numbers. This number is either 1, 2, or 3. If alpha I and alpha j are orthogonal, put no edge. Maybe I'll add that into my table. No edge between these vertices. Single bond, double bond, or triple bond, according to the cases in our table. And then finally I'm going to add a less than or a greater than I don't want to call that an arrow. It's not really an orientation. It's really an inequality in case alpha I and alpha j are of different lengths. So you do, well, I don't know. So if there's a single bond, they're the same length always. But it could be there's a double bond and then you orient that double bond, or it could be there's a triple bond, you orient the triple bond from I to j. If the length of alpha I is smaller than the length of alpha j, right? So this is really a less than sign. It's telling you which root is bigger, which root is smaller. Okay, so that's the Dynkin diagram, and so you can recover the Cartan matrix uniquely from the Dynkin diagram if you number the vertices of your Dynkin diagram 1 through L, you exactly recover the labeled alpha 1 through alpha L, the simple roots with that Cartan matrix. And from the Cartan matrix, as we've already discussed, you get the root system. Okay, so now we're down to just this problem of classifying all of these Dynkin diagrams that come from Cartan matrices of indecomposable root systems, and then that's the final classification theorem, which I can now at last state, though you kind of now know what it's going to be. The Dynkin diagrams classifying the indecomposable root systems up to isomorphism are exactly the Dynkin diagrams, which I've shown you before. AL, BL, CL, DL, EL, that's just 6, 7, 8, F4, and G2. And so let me finally draw these ones one more time. So L is always the rank, the number of vertices in the graph. So A is just a string. B is a string, except at the end when there's a double bond oriented that way. C is a string, except at the end there's a double bond oriented that way. D, well, there's a vertex of degree 3 at the end, so you have a little branch at the end. Then E's, they look like this, and then F4, and G2 is the one with a triple bond in there. Okay, so we saw all of these before. I showed you the AL root system. I just constructed it. For this, the Cartan matrix just is 2's down the diagonal. Cartan matrices always have 2's down the diagonals, and then minus 1's and 0's. B2 we've seen, that was our, so A2 is a special case of AL. B2 has this Cartan matrix, and G2 has this Cartan matrix, 2, minus 3, minus 1, 2. And I changed my numbering of my simple roots in my B2 picture earlier, so that these are now numbered in the way you expect, alpha 1, alpha 2. So I don't need to say very much more. Maybe it's just worth pointing out that there are some coincidences. A1 equals B1 equals C1, that's the rank 1 root system. So normally you just call it A1 and you don't let yourself use B1 or C1. And let me see, B2 is actually the same as C2. It's just that B2 goes that way and C2 goes that way, but up to switching alpha 1 and alpha 2, that's the same graph. And so now we're kind of just coming back, finally. I think I'm basically done with this chapter. It was a fast chapter, but I'm done with it. I'm coming back now to the classification of semi-simple Lie algebras. And we're going to see that out of our semi-simple Lie algebra, we've already constructed a root system. Now we've classified the root systems. So these Dinkin diagrams, they're going to label exactly the isomorphism classes of finite dimensional simple Lie algebras. And just, you kind of know what's going on. AL is going to be the special linear Lie algebra. BL is going to be the orthogonal one. CL is going to be symplectic. DL is going to be the even dimension orthogonal Lie algebra, SO2L. And so these coincidences in our Dinkin diagrams, this is SL2 being isomorphic to SO3 being isomorphic to SP2, and the B2 equals C2, well, this is the SO5 is actually isomorphic to SP4 of C. Those are the only coincidences between the simple Lie algebras. So I'm not proving classification theorem, but you can kind of maybe imagine how it goes. There's two steps. You first have to show that these are the only possibilities for Dinkin diagrams. You kind of have to find enough obstructions to all other possible diagrams so that you get these being the only possibilities. That's kind of just a case analysis, but it's not really very difficult. And then you actually have to show that indeed all of these Dinkin diagrams genuinely appear by actually constructing each of these root systems. So I've shown you the construction of AL. The only other ones I've constructed are, the only other indecomposable ones I've constructed are B2 and G2. But we'll see the other classical ones, BL, CL, DL, coming out of these classical Lie algebras. I mean, we've already really seen them, but I'll go back to those classical root systems. And E, F, and, well, G2 we've done, but E and F I'm not going to construct for you, but it's kind of elementary. F4, you need to work in a four-dimensional Euclidean space. The worst one is E8, where you need to explicitly write down a set of vectors in an 8-dimensional Euclidean space. It's fairly large, actually, but it's kind of just a direct, you literally just write it down, and then you check the axioms more or less by brute force. Okay, I'm going to finish this chapter. So you've got a glimpse of root systems. I've tried hard to prove all of the technical lemmas about Weil groups and length and height, because you certainly need those later on. When you're doing representation theory, that those lemmas will be crucial. But I tried to kind of skip the proofs of some of the actual theorems at the end, where I think you can take them on trust and get used to these examples.